message, even out of order, or you can acknowledge a whole sequence of messages. For example, you can decide that I want to receive a whole bunch of messages, I do something at once, and then I just acknowledge the last one, cumulatively. And finally, we have client-side stats in the client to help debug in the case that the application sees high latency, but on our hand, we don't see high latency. So now, a brief look at what the architecture of the system is. So we say that we have consumers that run our client library, and we have 2 layers in the system, and this is kind of the difference between other alternatives. We have 2 layers. One is the broker, and the broker is where the clients will have the interaction with. Clients will only interact with the brokers. And then we have bookies, so that is for storage. So bookies are Apache Bookkeeper storage nodes. So a client will interact with brokers, and brokers will store data in the bookies. And each broker basically will talk to many bookies. So there are like a few advantages of having this 2 layers approach. And so first of all is that the storage layer and the broker layer have different requirements. So in the storage layer, we care about the bottleneck is I/O capacity or storage capacity. So if you need more I/O, you can just add more bookies and you're done. But maybe you don't need more brokers, because for brokers the bottleneck is on the network, the NIC, and CPU. So if you're I/O bound, you can just add more bookies. If you are CPU bound, then you can add more brokers and have different configuration, hardware configuration. And the other advantage is that since the broker will have no durable state on them, it's very easy to shift traffic from one broker to the other. So if a topic at any given time is served by a single broker, but we can move topics from one broker to the other. Or like if all brokers are overloaded, we can just add more brokers and shift traffic automatically from these brokers to the new one. The same thing if the bookies are overloaded, we can just add more bookies and automatically they will ramp up in write traffic. So that's a very flexible solution. And okay, that's it. So, okay, now let's take a look at what happens inside a broker. This is a kind of an exploded view. So for each cluster that we have, typically we have one cluster per region. We have a set of brokers and bookies. We have Zookeeper cluster and a global Zookeeper cluster that I will cover later. So the main thing is that the client library is taking care of the service discovery. So whenever you create a producer, the client library internally will look up and will hit one broker, and that broker will respond that, okay, your topic is in broker X. Now the client library will open a connection to that broker directly, and we use a custom binary protocol for it. And in the broker, we have the dispatcher component, which is the component that is tasked of taking care of all the connections. And the more important part of the dispatcher and everything else inside the broker is that everything is async end-to-end. That the broker is designed to handle tens of thousands of connections, tens of thousands of topics, and there is nothing blocking in the whole flow. So the producer will do the service discovery, will figure out which broker will connect to the broker will perform authentication and authorization. If you're allowed, then your producer object will be created. At this point, you can send a message. You send a message, you will go to the dispatcher, and the dispatcher will forward it to the managed ledger. Managed ledger is a layer that we have built, and that represents the abstraction of the storage for a single topic. So for a single topic, what we need as an abstraction is the view of an infinite stream of messages, and with a number of consumers. And for each consumer, we need to know its own position. So that is the abstraction, and we have built this abstraction on top of Apache Bookkeeper. So Bookkeeper is we can create multiple logs, and that's what we maintain all this state inside managed ledger. So the message will be forwarded to the Bookkeeper client, which will forward it to the two bookies by default. And whenever these two bookies will acknowledge the persistence of this message, then the message will, the acknowledge will be propagated back to the producer. At the same time, the message will be dispatched immediately to the consumer, and it will be forwarded for replication to the other regions. Now, throughout all these back and forth flows, the message will never be copied. We use rough counted, so the same buffer that we read from one socket, we will write it into a different socket, and we will write it into a different socket. It's the same buffer. So finally, a word on global zookeeper. So this is a zookeeper quorum that we use and for configuration. And since we have multiple regions, it is very important for us to maintain the same configuration across all the regions. So we have a zookeeper quorum which spans 3 data centers with servers in the rest of the data centers, and this is where we store the configuration. So each region has the same view of the configuration. And finally, yes, the load balancer. The brokers also have a way to collect and report their own load and the load for each namespace group of topics. And with that information, what we do is that we try to make sure that the load is equal and traffic is spread evenly across all the brokers. So if there is any overloaded broker and there is any underloaded broker, then the load balancer that runs on one leader broker, it will decide to shift this traffic automatically from this broker to some other broker. And just a few words about Bookkeeper. So we say that we use Bookkeeper. We haven't really said what Bookkeeper is. So just a very short introduction. So by its own word, Bookkeeper is a replicated log service. What does that mean? That I can create a log and append entries into this log, and these entries will be replicated across n replicas. And if I crash, I can just replay the same log. And the main feature that Bookkeeper offers is that it is consistent. So no matter which kind of crash I have, I will always read the same sequence of entries after I crash. And the other feature is durability. So why is that a good choice for implementing a Pulsar service? The first thing is that we have our abstraction is an infinite stream of data, and a log structure is very good for us. And Bookkeeper is very efficiently in storing sequential data. Of course, we have to create multiple of these ledgers because you cannot delete a ledger in its entirety. So over time, for each topic, we keep creating new ledger and close the current one, roll over, create a new one, and then when all the consumers are done, then we can delete all the ledgers and keep moving on like this. So Bookkeeper, since we have these 2 layers and we keep creating new ledgers over time, the write rate across all the bookies is almost perfectly equalized. Each bookie will have the same amount of writes, and when there is some read traffic, it will be spread across as well. And there is a very good isolation between write and reads because of the storage architecture of Bookkeeper. And finally, Bookkeeper has a very flexible model for with which you can apply different trades-off when deciding how to write. For example, you can enable striping across multiple bookies so that you can have more throughput, or you can write 3 copies and wait for 2 acts, so you have lower latencies, and you can mix and match all these parameters. And you can configure that from Pulsar directly. So how does Bookkeeper store the data? So we talk about this is most of the time this data has to be durably stored because we don't want to lose any data in case of any crash. typically this data has a very different lifespan. Most of the time it can be deleted very quickly, within a few minutes. Sometimes we have to retain them for multiple days. So, first thing, a single bookie can serve thousands of ledgers. Actually, we tested up to hundreds of thousands of ledgers per single bookie. So it needs to have a way to multiplex all this data in some way. We cannot use these many files on the disk. So, and we want to have low latency. So to have low latency, what we use is that we have two different devices. One is a journal, which is with a red group dedicated for that. And whenever a new write comes in, it will be synced on the journal, just append only. We never read from it unless the book crashes. And we will do group commit and sync the data on disk. And at the same time, the data will be inserted into a write cache, which is in memory in the application, in the bookie application. And that's it. Your write can be acknowledged. It is durable because of the journal. Now, in background, this write cache will be flashed periodically on the disk, on a different device. When it is flashed, typically we use 1 minute intervals for that. And so we flash that write cache. First, we sort all the entries by letter ID, entry ID, so that we have sequential data on the disk. And we write this data into these entry logs, which are big files, 2 GB files, with entries for multiple logs. But for each flash interval, for each 1 minute, all the entries for a same topic would be sequentially stored on the disk. And after that, then we have an index, which we keep in RocksDB, and basically that maps that for each ledger ID and entry ID, what is the offset on the disk for that. So the sorting part is especially important because whenever we read, we only read from these bookies whenever we have backlog training. That means that you were not able to consume for an hour. Now you're consuming this backup and you want to drain all this backlog as fast as possible. And for that as fast as possible, you want to have the less IOPS that you can. So having a data separation on disk, we can leverage that also with our read-ahead cache. We just read thousands of entries and put that in memory. And we bet on the fact that if you read one entry, you're going to read all the next entries after that. And that's, last thing, so typically these two devices architecture also allow us to keep 2 different types of these. So for journal, typically we use SSDs to have low async latency, and for ledger storage we typically use HDDs to have higher storage capacity. And since the reads will be sequential, that's also very good throughput. Now, just a brief look. We've done a lot of tests. This is just a very small example of the test that you have done. So this is the publish latency on a single topic, single producer. There are no partitions, so this is a strong ordering, and this is with batching enabled. And we tested with different message sizes. So what we can see is that the 99% latency when publishing, it is across 4.5 milliseconds roughly, and that holds up until we hit some bottleneck. In this case, for example, the red line is the 1 KB. It maxes out at 130 megabytes per second, 130,000 messages per second on a single topic, and that's when a single bookie, the writes on the journal max out. We could use striping there, but to extend that throughput a bit. For 100 bytes, the cap is around 750K messages per second, and for 10 bytes is around 1.8 million messages per second. And there, the bottleneck typically is on the client library side. There's That's when contention comes and kicks in. But that's way beyond what we have need on a single topic. Finally, so this is an open source project. You can check it out, please test it, and give us feedback. If you have more in-depth questions, we are very happy to answer that. And there are too many links there. And we are very excited to see what other people wanted to use it for and see. And finally, we are hiring as well. So if you want to work on these big systems, we have open position for that. And that's it. Thank you.
So we have the floor open for questions now. Any questions? Okay, if not, thank you, Matteo. Let's have a clap from him. And thank you, everybody, for coming in and for coming in today. We look forward for your presence at a future hub. Thank you.